All right, so today we're going to look at logarithms. And before we begin, I'm going to go back to our main page. I'm going to go into lecture notes. Okay, and I believe it's 5.4. All right, and we're going to talk about logarithms. And first we'll just talk about the log function itself. And the last time we met, we talked about the exponential function. And the exponential function and the logarithm function, okay, are both what we call transcendental functions. And this logarithmic function is written as the log base a, and this is read as f of x is equal to the log base a of x, where a, right, has to be greater than 1. So a is your base. X is actually called the argument of your logarithm. All right, so here we have an example of a logarithmic graph. So notice the graph on the left is, as you read this from left to right, as you read graph, notice that the graph is ascending, it's going up. And just some facts about the logarithmic function: it's increasing, it's continuous on the entire domain. So remember that a function is continuous if you can trace if you can put your pencil on the graph and trace the entire graph without removing your pencil from the paper. The y-axis is the vertical asymptote. And then here are a couple of points that the graph passes through. Okay, a to the negative first comma negative 1, 1 comma 0, and a comma 1. All right, we also have another type logarithm, just as we had exponential function, where our base is in between 0 and 1. So if your log has a base in between 0 and 1, notice that on the left, this is the graph that it takes on. As you read this graph from left to right, it decreases. All right, and it's also, just kind of reading the bullet points here, it's decreasing, it's also continuous, it also has a vertical asymptote, and here are some of the points that it passes through. Now, graphs aren't really going to be a big part of our course. Hey, but the main thing on these first two slides are just the functions in themselves. Okay, I just thought there was some more information about logarithms. All right, so there is a relationship between a logarithm and an exponential equation, okay, or an exponent. So in log form, we have y is equal to the log base a of x. We can rewrite any logarithm as an exponent. So the way that this would be written is a raised to the power of y is equal to x. Okay, so this is actually a convergent formula. And you may ask, why would we want to change a logarithm to an exponent? Well, because when you're asked to solve a logarithmic equation, you must change your logarithm to an exponent and then solve the exponent. So we talked about how to solve an exponent. We can solve an exponent by using a change of base right? Once we make the bases exactly the same, we can drop the base and we can solve, set the exponents equal and solve. All right, so here's some examples. We want to convert to an exponent. So we have log base 2 of 8 is equal to 3. Right? And we want to convert this to an exponent. So when you're converting a logarithm to an exponent, the first thing, keep in mind that the base of your log, so here the base is 2, would also be the base of your exponent. Right? So since the base of my log is 2, the base of my exponent is 2. We talked about in the setup for a logarithm that you have a base, and this 8, I'm going to kind of temporarily put that in a set of parentheses. This is called your argument. Right? So if you ever hear me say, what's the argument of the logarithm? Right, in this particular case, 8 served as the argument. So if we look at the formula at the top, we can take the base of our logarithm, which is 2, that's the base of our exponent. We can raise it to whatever our logarithm is equal to, which is 3. And we can set that equal to the argument, which is 8. So we have just written log base 2 of 8 equal to 3 as 2 to the 3rd power is equal to 8. You can also go the other way around. Okay, we're going to solve the logarithm. So we have log base x of 2 is equal to 4. And we're asked to solve the logarithm. So in order to solve, excuse me, this should be 16, I'm sorry. So I'm going to rewrite that as the log base x of 16 is equal to 4. Okay. So in order to solve any logarithm, we must convert the log to an exponent. All right, so I'm going to use that previous formula. The log of my, the base of my log is x. Therefore, the base of my exponent is x. I'm going to raise x to the 4th power. And I'm going to set that equal to 16. So x is what number raised to the 4th power is equal to 16. So we know that 2 raised to the 4th power is equal to 16. Therefore, x should equal to 2. Right. So to solve any logarithm, you must first convert to an exponent, and then we're going to solve the exponent. Next thing we're going to take a look at is the domain of a log function. So here we give an example, y is equal to the log So I guess before I actually talk about domain, let's talk about the types of logarithms. So there are two common types of logarithms. One is called a common logarithm, and common logarithms have a base 10. Have an understood base 10. Okay, because on some of the logs you're going to see they're not going to have a base. If your log does not have a base, then it's assumed to have a base 10, right? So here's some examples of common logs. right? So say if we see something that says the log of 3, right? Notice that we don't see a base. The base is understood to be a base 10. Sometimes you may see log written in lowercase letters. Sometimes you may see it written in capital letters. These things are one and the same. Your calculator can evaluate common logs. We also have something called natural logs. And natural logs have an understood base E. So here's an example. So let's say that we have the natural log. So you're never really going to see this, right? Log base E of 3. But what you will see is ln3. Right? So whenever you see that ln, that's a logarithm that has an understood base of exponential E. If you take a look at your calculator, and I'm just going to bring mine up. You'll notice that we do have the common log, which is the log log, right? So I'm just going to put in the log of 3, right? And that's 0.47. I'm going to put in the natural log of 3. Okay, notice I get 2 different complete values. All right, so now we're going to talk about domain. And I'm just going to move this down some. All right, so we're asked to find the domain for y is equal to log of 6 minus 2x. So notice that there is no base written, so this is an understood common log. Now, in order to find the domain for any logarithmic function, you should take the argument. So in this case, the argument is 6 minus 2x. And we're going to set that to greater than 0. The reason why we set this to greater than 0 is that from our setup, notice that your base has to either be greater than 1 or it has to be in between 0 and 1, okay, depending upon what kind of log we have. So therefore, our domain, we simply take the argument, set that equal, we'll set that greater than 0, and we solve. So I'm going to solve. So I'm going to subtract 6 from both sides. Okay. The next thing I'm going to do is divide both sides by a negative. So you just want to remember this fact. When you multiply or divide an inequality by a negative number, you must reverse the sign. Okay. So whenever you multiply or divide an inequality by a negative number, you must reverse the sign. So in this case, we want to divide both sides by -2. So I'm dividing by a negative, so the first thing I'm going to do is reverse the sign. So x is less than or equal to 3. So we want to rewrite this in interval notation. Okay, so just to go back through that, I'm just going to draw a line graph centered at 3. Negative infinity is to the left. Positive infinity is to the right. We want all numbers that are less than 3. Right, so our parenthesis faces the left. Our line extends toward the left. Right, so we can write this as the open interval from negative infinity to 3. All right. Okay, next we're going to talk about the properties of logarithms. All right, so we're going to talk about the 3 properties: the product rule, the quotient rule, and the power rule. All right, so here is the product rule. Okay, and for these rules, we're simply going to use the common log, but they apply to all bases for all logs. We have the log of x plus the log of y. Well, I'm actually going to write this in reverse. The log of x times y, is equal to the log of x plus the log of y. And I'm actually going to use a number example. So this says that if you're dealing with logarithms, you can take a product and rewrite a product as a sum. So here is an example. I'm going to use the log of so in my calculator, we're going to evaluate the log of 8. All right, just to put some numbers to these formulas and just to show why they're true. All right, so the log of 8 is 0.903. So if this rule is correct, it says that any 2 numbers that I can multiply to get an 8 in the log, I can add. So if we just take a look at 8, I can get 8 by 1 times 8 or by 2 times 4, right? So I could rewrite the log of 8 as the log of 1 plus the log of 8. And they should have the same exact value. So I'm going to do that on a calculator. So I'm going to put in the log of 1 plus the log of 8. Right, and we get 0.903. We get the same value. Okay, well, you say, well, 1 plus 8 is not really 8. But we're not dealing with a 1 and an 8. We're dealing with a log 1 and a log 8. I could also write the log of 8 as the log of 2 plus the log of 4. So if I put that in the calculator, the log of 2 plus the log of 4, right, I get 0.903. Okay, the reason why I show you this is because when we're dealing with the log of, let's say, z and f or whatever, since you don't actually know the value of c, you don't actually know the value of f, but you can use these properties. Next, we're going to take a look at the quotient rule. And the quotient rule for radicals says that the log of x divided by y, that's equal to log x minus log y. So you could take a quotient and write it as a difference. Right? So just be specific that your numerator, right, must go first minus the log of your denominator. So we're going to use that same 8 as an example. So what are the different numbers I can divide to get 8? Well, that could be 8 divided by 1, 16 divided by 2 will give me 8, 24 divided by 3 will give me 8. That'll keep on going. So I'm going to take this second one. I'm going to take 16 divided by 2. So I'm going to take the log of 8, and I'm going to write that as the log of 16 minus the log of 2. Right? So now 16 minus 2 is not 8, but I'm not dealing with a 16. I'm not dealing with a 2. I'm dealing with log 16 and log 2. So I'm going to put that into the calculator. The log of 16 minus the log of 2, and I get that same value, 0.903. You could do that for 8 divided by 1. You could also do that for 24 divided by 3. And lastly, we're going to look at something called a power rule. And it says that the log of a raised to the power of r, that's equal to r times the log of a. And this formula is not very intuitive because it seems like the only thing you're really doing is taking your power and writing it as a multiplier. Okay. But let's see how this one works in action. So I'm going to take the same log of 8, right? But instead of writing 8 as 8, I'm going to write 8 as 2 raised to the third power. Right? Because 2 raised to the third power is 8. So now if this power rule is true, I can take the power, which is 3. I can write that as a multiplier. Right? So I could rewrite the log of 8 as 3 times the log of 2. So I'm going to put that into the calculator. So I have 3 times the log of 2. Right? And notice we have the same value, 0.903. All right, so let's take a look at an example using the properties. So we have the log of x to the 8th power y squared divided by z to the 6th power. Okay. And I forget which problem this is similar to. All right, and we want to rewrite it, and we're going to use those properties. Okay. So first thing is, notice that I have two operations. There is a multiplication in the numerator, right, because that's x to the 8 times y squared. So I can rewrite that product as a sum. And then I have a division divided by z to the 6th power. I can rewrite the division as a minus. Okay. So I'm going to start in the numerator. So I'm going to write this out as, and I'm just going to write out all the steps. The log of x to the 8th power plus the log of y squared. Right? Because I can rewrite that product as a sum minus the log of z to the 6th power. Right? So if you're dealing with a fractional bar, anything in the numerator is a plus, anything in the denominator is a minus. Okay. So I've used the product and the sum rule. Next, I'm going to use the power rule. Right? I want to take all of my exponents and write them as multipliers. So for this first term, I'm going to write it as 8 times the log of x. For the second term, I'm going to write it as plus 2 times the log of y. And for the last term, I'm going to write this as plus negative 6 times the log of z. And I believe that is similar to number 17. Okay, we're going to work with natural logs. Okay, now these three rules, they work for common logs, natural logs, any logs with the same base. So let's take a look at this example. Okay, write as a simple log. The natural log of 7 plus the natural log of x plus the natural log of y. And we're asked to write this as a single logarithm. All right, so we're basically going to use the formula. All right. So notice that these formulas do work in reverse. All right. So if I go back up, so that means the log of x plus the log of y, that's equal to the log of x times y. So I can rewrite the log of the natural log of 7 plus the natural log of x plus the natural log of y as the natural log of 7 times x times y. Right? I can rewrite each sum as a product. Okay, we'll take a look at this one. All right, so the directions are the same. We want to condense it to a single logarithm. 2 log x plus 3 times a log of x plus 3. Okay, and we're asked to write this as a single log. All right, so here again, we're going to use the properties from earlier. So notice here that we have a plus, right? So that plus indicates a product. So I'm going to write this as I guess before I do that, I'm going to use the power rule in reverse first. So I'm going to take these multipliers and I'm going to write the multipliers as powers. So I'm going to take this first term and I'm going to write that as a log of x squared. Right? Because remember that power rule says we can write a exponent as a multiplier and then vice versa. You can write a multiplier as an exponent. Plus the log of x plus 3 raised to the third power. So I've used the power rule in reverse. So now I'm going to rewrite that sum as a product. So I can write this out as a log of x squared times x plus 3 cubed. Right. So I use the power rule first in reverse, and then we use the product rule. And I'm going to check the next section to see what's in